So, guten Morgen, meine Damen und Herren, meine Kinder. Gehen wir weiter, ein bisschen weiter mit A here, yes. So, let's go farther with our concept of the standard potential for a reaction, right? We just finished talking about how we can adjust our standard reaction potential to non-standard conditions. And there's a special case that we can make, and it's called a concentration cell. All right. So let's talk about a concentration cell right here under B here. Let's go with B. Concentration cell. Concentration cell. So in this kind of here, let me draw you a picture of a concentration cell. All right. So here's our illustration. So let's take. Well, we have a problem coming up. So, I'll just make one up. Let's say we have illustration, right? Because if not, concentration in a cell will make you ill, right? Illustration. So let's say that we have two zinc cells, right? So I have a zinc electrode in a zinc solution, and I'm going to take another zinc electrode and I'm going to put it in another solution. Oops, can't be that way. I got to have my solution, my electrode in my solution. Good. Okay, and we're going to connect these, and this is zinc, and this is zinc, and let's say that this is zinc solution, and let's say that this is a zinc solution. All right, cool. Now, let's though play around a little bit with, let's say that my concentration here is 1.0 molar, and let's say that this is 0.1 molar. Oops, it's making two sig figs just for the fun of it. Good. So what do you think is going to happen? Do you think anything is going to happen? I think something's going to happen, right? It doesn't make sense that these two are different. So what's going to happen in the reaction? The reaction is going to try to bring these two things closer. So now here's my question. So if I have zinc reducing, right? What happens to my concentration of zinc when zinc reduces? My concentration is going to go up or down. Well, I'm going to be taking, this is aqueous, right? So when I reduce zinc, I am taking zinc out of solution and I'm making it solid, meaning my zinc concentration is going to go down, which should mean that this side over here, this side is going to be my reduction half cell, right? And which would mean that this side needs to be my oxidation half cell, right? And when I'm oxidizing right over here, so this is the reaction that's occurring here. Maybe I'll clean this up a bit. Let me clean that up with my magic finger. Yes, wow, beautiful. So this is my reduction half cell, meaning I'm going to take Zn 2 plus aqueous plus 2 electrons. It's going to go to Zn solid. And what's going to happen in my oxidation half cell? My Zn solid is going to go to Zn 2 plus 2 electrons, right? Aqueous. Good. And for the heck of it, let's go ahead and write the total equation. So what do I really have? I have Zn 2 plus aqueous, but let's go ahead and write down the concentration here. Oops, 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 oops. 1 molar. And my 2 electrons are going to cancel, and my zinc solid, I'm going to have a plus a zinc solid here, which we could really say is going to cancel, couldn't we? Because that's a zinc solid. Yeah, I think that's all going to cancel, right? And all I get is, I get Zn 2 plus going to aqueous, what? 0.10 molar. Good. And so that's really what's going on in the reaction. Now, of course, because these concentrations, woo, man, just got air sick. Because these concentrations are different, I do have a driving force, right? I have an electromotive force that is driving those towards the same concentration, meaning I really have a non-standard cell potential question. So that would mean what? E is equal to E prime minus RT over NF, natural log of Q, right? Cool. What's my E prime? Well, I have aluminum 3 going to aluminum, and then I have, not aluminum, what am I talking about? I have zinc 2 plus going to zinc, and I have zinc going to zinc 2 plus, which means what is happening at my cathode? What is happening at my cathode? This is happening at my cathode. This is happening at my anode, meaning my E prime for this is equal to 0, folks, right? My half cell potentials are the same, but just one I'm subtracting from the other, which means that my E for this cell is just simply negative RT over NF, natural log of Q, right? Now, how many electrons are we transferring in this reaction? 2. So we have a negative 8.314 joules per mole Kelvin times my 298 Kelvin over 6 times 96485 joules per, that's a joule, by the way, per volt mole, right? Times the natural log. Now, what's Q? My Q is my concentration of my zinc, right? Concentration of my zinc. Which zinc? The 0.01, meaning I would call it my dilute. Excuse me. My dilute 0.10 over the concentration of my concentrate 1.0, right? Good. So, to get the answer to this, right, it would be, here we go, 0.1, take the natural log of that, natural log of my 0.1, natural log of 0.1, right, times 298 times 8.314 divided by 6 divided by 96485, and I get a negative of that, so I get a 9.8 times 10, see, 9.8, yeah, I guess 9.8. I get 9.8 times 10 to the minus third volts. That's my driving force. All right? Now, just to summarize, what is my equation? It is that my E is equal to negative RT over NF, natural log, not instead of Q, we're going to say my dilute to its coefficient over my concentrate to its coefficient. All right, does that make some sense, y'all? Yeah, good. So this would be my adjustment, or this would be the way I would solve a problem using a concentration cell. So let's take a look at a concentration cell, although I kind of just did one, didn't I? We'll come back to that one in a sec, sorry. So here's our concentration cell. I have nickel concentration cell. I have 10 and 0.001. So I'm going to draw the cell. Are you ready? Here, you guys draw the cell first, and I'll come back and help you. Okay, you guys are done. So I'd have a nickel electrode, and I'd have a nickel electrode. I'm going to connect those with a wire. I'm going to put them in some nickel solution, nickel 2 solution. Oh, you know what I forgot? Oh, I need my bridge always. Oh man, I've been forgetting my bridge. I wouldn't function without my bridge. So this is going to be, I'm going to call this my 0.0010 molar, and I'm going to call this my 1.0 molar, right? And so then my E is going to be equal to negative RT over NF natural log of my Q. And so how many electrons are going to be transferred? Well, I have nickel going to nickel 2, so that means 2 electrons are going to be transferred. So this would be equal to, I'm going to move this down here, yoink. This would be equal to what? Negative 8.314 joules per mole Kelvin times 298, I'm assuming this is at standard temp, over my N, which is equal to 2 times 96485, natural log of my dilute, 0.0010, to what's the coefficient? No, it's just going to be a coefficient of 1, right? Over the concentration of my concentrate, 1.0. All right, cool. By the way, if you're getting a negative value, you did something wrong because there should be a driving force here, right? Natural log of 0.001, cool, divided by 1, yeah, I can do that, times 298 times 8.314 divided by 2 divided by 96485, and I get a negative, but then it's a negative. I get a 0.089 volts is my cell potential. All right, wonderful. You guys do this one. Oh, look at that, zinc. You guys do this one, bring me back. All right, that wasn't so hard, was it? Here we go, let's draw our cell, let's identify everything. So I'm going to need more space to do that since they want me to identify stuff, but we kind of did it already, didn't we? So here's a cell, and bridge, salt bridge, cell. Let's put in some electrodes, right? Let's hook them up. These are both zinc, and let's put some zinc solution in here. So here I have zinc solution, and here I have zinc solution, and which, you guys care which is which? Let's put over here, let's say that this is 0.000375 molar, and over here is what? 1.35 molar. 1.35 molar. And what do I know? I know this is going to have to come down. And so if that's going to have to come down, I'm going to have to pull zinc out of solution, right? So that means my zinc 2 plus is going to have to reduce to my zinc solid, right? Aqueous. Which means on this side I have the opposite going. I have zinc solid coming from my anode. This is my anode, my anode, and my cathode, fat cat, right? The fat cat, the anode, the cathode gains weight, gains mass. Red cat, I think. Fat cat too. Red cat, fat cat. Cool. And over here then I have my zinc solid going to zinc 2 aqueous plus 2 electrons. Cool. So that's what I have going on. That's my picture, my anode, my cathode. And so now, what do we know? E is equal to negative RT over NF, my natural log of Q. And so that would mean my negative 8.314 joules per volt mole Kelvin times 298 Kelvin over N. What is my N this time? Well, 2 electrons. So N is equal to 2 this time. By the way, N's don't always have to be 2 or 6. It just kind of, that's the way it worked out on these questions. 96485 joules per volt mole, right? Times the natural log of my dilute. What was my dilute? 0.000375 over my concentrate, 135. There we go. Let's run our magic calculator, and I get the natural log of 0.000375 divided by 1.35, close, times 298 times 8.314 divided by 2 divided by 96485, and I get a 0.105 as my answer. How's that, folks? Cool, cool. Hey, it looks like I skipped a couple problems, so let's go back and take care of those before we say adios, amigos. All right, so what do I have going on here? I have voltaic cell, and you can see the only difference here is they dropped in a gas. Now, this is weird. All right, I don't completely understand it, but I know it works in this case. So usually we're used to Q's being either all pressures or all aqueous. But when we're doing this kind of a problem, our Q is going to include both. So when I'm writing my Q for this question, my Q is going to be equal to the concentration of zinc times the partial pressure of my hydrogen. Both of those have coefficients to the 1, right? Divided by the concentration of my hydrogen squared. So that's what the Q is going to be for here. All right, so now let's work this. Are you ready? Here we go. So I'm going to work it down here because I need space. You've seen me work. What do I have going on here? What is oxidizing? I have my zinc going from 0 to 2 plus, so zinc is oxidizing. So my E prime is going to be equal to my standard reduction potential for my hydrogen, and we all love that because we know it's 0, right? Minus the standard reduction potential for my zinc, and I should know it now, but it's like a negative 7, isn't it? A 0.7, but I'll have to look at it. Let's go check that out. So we have 0 minus negative 0.776 maybe. Let's see. You guys believe me? Zinc, it's at the bottom. Ooh, so close. Negative 0.763. 0.763. Negative 0.763. Got to write that down or else I'll forget in the 30 seconds, 10 seconds, 5 seconds. It takes me to get to this question. Right here, good. Oh, what is it? I almost forgot already. Oh, good thing I wrote it down. Negative 0.763 volts, right? So my E prime is going to be a positive 0.763 volts. Since it's positive, we know that that is spontaneous in the forward direction. So then my E is going to equal my E prime minus, what did I say? RT over NF, natural log of Q. So let's drop in some numbers here. Are you ready? Here we go. This is what? 0.763, that's a 6, volts, minus R, 8.314 joules per mole Kelvin times 298 Kelvin, right? Over N. Now, what's my N? I have to look at my reaction. Well, I have one zinc going from 0 to +2, and so that means I have 2 electrons transferring, right? Or I have 2 H pluses going to 1, so I have 2 plus 1s going to a 0, and that means 1 electron times 2. So yeah, it's 2 electrons that are transferred. 2 times 96485 joules per volt mole, and natural log of my zinc. Here's my Q up here. We already know this, so I can just drop in my values. My zinc is 1 molar times my partial pressure of my hydrogen is 1 atmosphere divided by the concentration of my, oh boy, they made this hard. I didn't read the question. H plus squared, right? What did they do, those donkeys? They gave us my E. Ah! That means I have to do some math. How dare they? So that means this is 0.45. Yikes, this is 0.45 volts. All right, so I'm going to get rid of all this. Oh, I have the magic finger, so I can get rid of that, just like that. And now I have all this. I have to solve for my H plus. Are you ready? This is going to be a little painful. Let's see if I can do it. All right, you ready? You trust me? Okay, I'm going to take 0.45. I'm going to subtract 0.763. And what do I get? I get negative 0.313 is equal to negative all this stuff. I'm going to calculate all that stuff right now. Are you ready? 8.314 times 298 divided by 2 divided by 96485. So I get that's equal to a negative 0.0128 natural log of 1 over my H plus squared, right? So then what am I going to do? Divide this by both sides. I'm going to divide by negative 0.0128. Divide that by negative 0.0128. This all becomes 1. And I'll have the natural log of 1 over H plus squared, right? Okay, you ready? Oh, so I'm going to take 0.313 and divide that by 0.0128, and I get 24.45. What do I want to do then? I want to, oh boy, that looks bad, doesn't it? We'll see. I'm going to do the E, right? So E to the 24.45 is equal to 1 over H plus squared. So I get 4.167 times 10 to the 10th is equal to 1 over H plus squared. I take the inverse of that. And so I get H plus squared is equal to 2.399 times 10 to the minus 11th. Take the square root of that. Oh, bummer. I did something wrong. Let's try that again. So I have my 2. Okay, good. So I got that. So now what do I want to do? I want to take the square root of that value, and I get 4.9 times 10 to the minus 6 molar. All right, you guys trust me on that? Let's run those numbers once again just to make sure I got this right. 0.45, got it. I'm going to subtract 0.763. That gives me a number. I'm going to multiply that by a negative 1. Okay, times 2 times 96485 divided by 8.314 divided by 298. Good. That gives me 24.3. I got 24.37 this time. Could be rounding error there. Okay. And then I'm going to take the E of that. So then I'm going to take the E of that, and I get 3.8 times 10 to the minus 10th. I'm going to invert that and take the square root of that. And I get 5.1 times 10 to the minus 6. So if you don't round, you're going to get this number. If you round, you get that number. Okay, it looks like I did it. Looks like I did it right. All right, so you guys do it. You do the next one. Bring me back when you're ready. All right, so I mean, you essentially do what I did already. I'm going to erase a lot of this stuff so that I can just work it right here, if that's okay with you. I'm going to go good. Ooh, beautiful. I love that. Here we go. Woohoo! Great. And I'm even going to get rid of this. But I'm going to leave that one dot to bother you type A people. All right, here we go. We know that my, oh boy, oh yeah, I remember what my standard cell is. My E prime was equal to, what did we say? 0.763 volts, right? Because we still have the same cell. So I have 0.542 volts equals 0.763 volts minus R 8.314 joules per volt mole. Nope, joules per mole Kelvin. Got to make sure I get my right units. Times 298 Kelvin over N. My N we said was 2 this time. 96485 joules per volt mole. There it is, right? Natural log of, what did we say? Concentration of my zinc. What's the concentration of my zinc? 0.10 times the pressure. What's my pressure? Where is my pressure? Oh, there's my pressure. 1 molar over the concentration of my H plus squared, right? Good. So let's run the numbers. So I have 0.542. I'm going to subtract 0.763, negative, divide that by negative 1. That gives me 0.221 times 2 times 96485 divided by 8.314 divided by 298. And what I get is 17.21 is equal to the natural log of 0.1 over H plus squared. So I'm going to do the E, magic E, let's put in the magic E. E to the 17.21 is equal to 0.1 over my H plus squared. Okay, so let's take the E. And I get, oh my gosh, big number. Something like 2.98 times 10 to the 1, 2, 3, 4, 5, 6, 7. 10 to the 7 is equal to 0.1 over H plus squared. So I'm going to divide both sides by 0.1, divide that by 0.1, and I get same thing, right? 2.98 times 10 to the 8th is equal to 1 over H plus squared. So what am I going to do? I'm going to take the inverse. So when I take the inverse, right, I flip everything on their heads, and I get 3.345 times 10 to the minus 9th is equal to my H plus squared. Take the square root of that. And I get my H plus concentration to be equal to 5.78 times 10 to the minus fifth, but they want my pH, so that means I take the negative log of that, take the negative log of that, negative log of my answer, and it should be between what, 4 and 5, almost in the middle. How about 4.6? Oh, 4 point, I have no idea in sig figs, quite honestly. 2, oh, it looks like 2, it looks like 1 sig fig, doesn't it? Yeah, I'm going to guess there's 1 sig fig out of this. So 4.2, but if you had 4.23, that's my pH. Holy moly! All right, that will do it for today, or at least for this session. We will finish up the chapter next time. Bye.